what is it, the 20th. So first and foremost, the one number comment I have is some work. So here's what you guys need to do. Please turn in your assignments. Now, I don't care how correct they are or how much is completed. I want you to turn in whatever you have now. Let me look at it. Let me comment. Let me give you some pointers and advice. Don't worry if the problems aren't all correct. That's irrelevant right now. Turn in whatever you got on all these assignments. That's the most important thing. Turn something in, and then we'll go from there. There's too many missing assignments out there. So if you guys can turn that stuff in ASAP. And again, I don't care how correct it is. I don't care how complete it is. What I'd like you to do is turn some things in, preferably through Canvas. But if you can't, I mean, obviously you can email me, but it's much easier for me to get things done through Canvas. The next thing I want to remind you is I posted a new practice set last week. Hopefully you got some chance to look at it. We're going to do some problems from that right now. Well, not necessarily. Well, yeah, we will. And then we're going to talk about the connection of this stuff with sort of what we've been talking about. While I pull up the homework for my own self to see which one I gave you, does anybody have any questions or comments about anything at all? Going once? Going twice? My computer's being very slow right now. Okay, so sweet. What we want to do is we want to do some problems that help you see why these things we talked about last week, these Fourier series, are pretty cool. So let's do that. So let's remind ourselves of what we're doing. So last week, what we did is we introduced a very important and useful tool. And that was called Fourier series. So there's a couple ways that you can motivate these things. One way is from the physical sort of historical standpoint of where they came from when this scientist Joseph Fourier was studying heat, and he has this equation that he believes describes how heat behaves. So if you're not quite sure what I mean by how heat behaves, imagine you have like a metal rod, and imagine that it has an initial temperature, So imagine you have a device that can measure the temperature of the rod, and then if I put a heat source on it, as you guys know, if you take like a metal, take some metal object like a fork or a knife and you heat one end, eventually the whole thing heats up. And so what Fourier was trying to understand and study was, how does heat behave? Anyhow, he arrives at this equation called, creatively enough, the heat equation. And when he solves it, he uses this very fascinating way of solving it that is similar to something we learned in Calc 2, but it's a little more complicated. If you remember in Calc 2, we studied this thing called separation of variables. When we studied these I shouldn't say separation of variables. Well, yeah, we had these separable equations, and we even solved a couple of those in this class. And so what happens is, in more complicated equations, you have more than one variable, and these are called partial differential equations. And one way of solving them is this sort of similar idea of separating variables. Nonetheless, when you do this, you arrive at a solution that is a series. And so this series turns out to be a very useful series. And as we talked about last class, it's called a Fourier series. And here's another way, I should say. of sort of introducing the Fourier series is solely from a mathematical standpoint. And that's what we did last class. We said, let's assume that this thing exists. What must it look like if it does exist? And now what we're going to do today is we're going to do we're going to do an example, and we're going to show you why these Fourier series are super useful from the mathematical standpoint. So let's do an example. So for homework, I asked you to do the Fourier series for 2 particular functions. Let's do one that's not on here, and I want to mimic this as much as I can with the homework problem, so you can follow along what I'm doing. Does anybody have a question first? Comment? So here we go. So if you remember last class, and it might be worth me showing you this picture one more time. Give me a second. I'm going to pull this up. Where did it go? Okay, cool. So if you remember last class, I showed you this picture. Where's it at? Where did it go? This picture right here. And what I want you to think about is think of this blue line and think of it as a signal, maybe on, off, on, off. And imagine reading it from left to right. And remember, what we want to do is, even from a geometric standpoint, the idea is can we approximate that graph of that blue thing with some nice smooth curve? And this is a similar problem to that of calculus 2 when we had power series, and more particularly, we studied Taylor series. And we said, given a continuous function that has all these derivatives, can we approximate it with polynomials? So now we're not approximating with polynomials, but we want to approximate with sine and cosine waves. And so we're going to show how this works, and we're going to recreate this picture. So that's what we want to do. Okay, so here's the example. What I want to do is I want to let f of x be the following function. So I want to let it be -1 when x is between 0 and -pi. And I want it to be +1 when x is greater than 0 but less than pi. So let's graph what this might look like. So here's our xy axis, and let's put pi here, and then let's put -pi here. And let's imagine that this is the height of 1, and then this is -1. So what does this graph look like? Well, we get out our blue. It's at height 1 between 0 and pi, and then it's at height -1 between, fix this, between -pi and 1. So this is a sort of similar to this blue picture I showed you from Wikipedia. You have -1 and then it jumps up to 1. Now, if you look at the homework problem, what you'll see is you'll say, the first thing I said is graph it on the interval -3 pi to 3 pi. And what this means by extending it periodically is just making the pattern repeat. So what would that mean? Well, let's extend out my XY axis. So if I want to extend it out, what I mean by that is let's think about this is going to be up to, so what's the next thing? This would be 2 pi. And then let's say 3 pi. So if I extend it out periodically, that means I'm listening, I'm following the same pattern. So then it looks like this. And then it looks like this. And then similarly, we would have the same pattern all the way out to negative 3 pi. Does anybody have a question about this?
And why is it -1 between pi and 2 pi?
We're just defining it that way. So, okay, so ignore everything to the right of pi at first. Notice where the function's defined. The function is just defined between negative pi and pi, correct?
Yep.
Right, now I'm saying let's extend it out further. How are we going to extend it out? Well, there's no rule for, I don't have a rule for f of x when x is like bigger than pi, right? I don't have a rule. So what I'm saying is just repeat the pattern. So between pi and 2 pi, we'll just shift it to the right. We'll shift the graph to the right, and then a period of 2 pi. I mean, think about how sine and cosine are defined. It's the same exact way, right? Look at sine. You really only need to define it between negative pi and pi. Everything else is just the pattern repeated. I don't know, does that make sense? It's usually weird to think of it at first, but that's kind of the idea.
Mm-hmm.
With that?
Yep.
Okay, cool. All right. So what we want to do now is we now want to, once we have the idea of what the graph looks like, what we want to do is we want to first compute the Fourier coefficients, and then we want to compute the Fourier series, and then we want to look at the graph of this creature and put it on the same XY axis as some of the partial sums. And we'll see what pretty coolness happens from that. All right, so let's do that. So we go to the next page. We want to compute the Fourier coefficients, which are a sub n and b sub n. And so we have formulas for these things that you might not have memorized right now, and that's okay. You just look them up. So what was a sub n? Well, a sub n, by definition, is the 1 over pi times the integral negative pi to pi. And then it's our function. So it's our function f of x times the cosine evaluated at nx dx. Now remember, this is true for n equals 0, n equals 1, n equals 2, n equals 3, so on and so forth. Okay, so what is our function f of x here? Well, it is piecewise defined. So what we need to do is we need to recognize that this creature is 1 over pi, and we're going to break the integral into two pieces. We're going to go from negative pi to 0. And on that interval, what is the function? The function is -1 times the cosine of nx. And then it's 1 over pi, and then we have to integrate over this integral where the function is just 1. Now, in the two, so again, why do I have to have two integrals here? Well, because my function is defined differently depending on what interval I am on. So from negative pi to 0, the function takes one rule because it's piecewise defined, and then on the other interval, it takes another rule. Now, there's a couple things that we can do right away for a shortcut. So we have this, we have to compute both of these integrals. But here's something that's real simple to sort of think about. When n is 0, we already know the cosine of 0 is what? The cosine of 0 is 1. So let's look at that case separately. So what is a sub 0? Well, a sub 0 is 1 over pi integral negative pi to 0 of negative 1 dx. And then that's plus 1 over pi integral 0 to pi of 1 dx. And when you integrate this, let's go real slow just so we don't get too brave. The integral of negative 1 becomes negative x evaluated from negative pi to 0 plus 1 over pi, and then the integral of x is, or excuse me, 1 is x, and we evaluate that from 0 to pi. And so if you plug this in, let's go very slowly because it's worth doing this. When you plug 0 in, you get 0. When you plug negative pi in, you get minus a minus a minus. So this is wild, right? So you end up getting what? So again, remember what the fundamental theorem of calculus says. It says it's you plug in the upper bound, then you subtract the lower bound. So this is 0 minus, what's the lower bound? Well, the lower bound is negative pi. Yikes. And then similarly up here, you have 1 over pi, and then this just becomes pi minus 0. So at the end of the day, a negative times a negative is positive times another negative is negative. So this becomes negative 1 plus 1, which is 0. And this is what you should expect, right? Go back to the picture. Part of the graph is under the curve, or is under the x-axis. The other half is above, so the negative area and the positive area cancel out. The net area is 0. Does anybody have a question about this? So what we found is a sub 0 is equal to 0. Okay, so what happens when n is not 0? What happens when n is in general? So for general n greater than or equal to 1, remember n is an integer. What is a sub n? Well, we already know this. It's 1 over pi, negative pi to 0, and then this is negative. So we'll put the minus sign out front. This is just cosine of nx dx. And then this is plus 1 over pi, the integral of 0 to pi, cosine of nx dx. Now, how do we integrate this cosine? Well, the integral of cosine of nx becomes, let's go carefully, 1 over n sine of nx between negative pi and 0. And then it's plus 1 over pi. And then, of course, it's 1 over n sine of nx between 0 and pi. Now, we talked about this last class. Remember this, and I believe, Abdullah, you asked about this. When I plug 0 in the sign, I get 0. Doesn't matter. Sine of 0 is always 0. And when I plug multiples of pi in, it's always 0. So this becomes negative 1 over n pi, and then it's sine of 0 minus the sine of negative n pi. And then this becomes 1 over n pi. And then the same sort of argument, this becomes n pi. Well, I got that backwards here. So this might take a moment since we're not so used to dealing with these more arbitrary terms. But the key observation is all 4 of these terms equal 0, equal 0, equal 0, equal 0. All of them. So what that tells us is that a sub n, the coefficient a sub n, is equal to 0. Now, here's a cool fact that is typically stated in a class like this. Anytime your function f is odd, do you guys remember way back in like algebra class you learned about even and odd functions? And when you were learning about symmetry and stuff like that? Well, here's a very cool fact. Anytime your function f, anytime it's odd, your a sub n's are always 0, always. And then if your function f is even, your b sub n's are 0. You can actually prove that. It's not difficult to do. But anyhow, this turns out to be 0. So that can save you a lot of time computing when you're doing things. Does anybody have a question about this? Okay, so let's do the b sub n's. So remember, b sub n is very similar. It's the integral 1 over pi, integral negative pi to pi of your function f. And then it's the sine of nx dx. And so here's something that's real clear. B sub 0 is equal to 0. Why? Well, since sine of 0 is equal to 0. So B sub 0 is always 0. If n is equal to 1 or greater than or equal to 1, B sub n, just like we did before, is going to be negative 1 over pi integral negative pi to 0 of sine of x, or nx dx, plus 1 over pi integral 0 to pi sine of nx dx. Okay, so now these integrals are slightly different than the ones before, but they're not difficult as long as you remember how sine and cosine behave at values of pi and at values of pi over 2. And so let's go to this next page. This becomes negative, what's the integral? So it's negative n pi, because you get that n, and this will be cosine of nx, but we have another negative here. So this one just becomes plus, and you're evaluated from negative pi to 0. And now the other one becomes minus 1 over n pi. So it looks like it's flipped from the previous problem. So what you might want to review, and this is, you might be getting sort of off track by this. I'm going to remind you that why these signs are the way they are is the integral of sine of nx dx. This is negative 1 over n cosine And then the integral of cosine, as we saw in the previous computing the a sub n's, this is positive 1 over n sine. So these are the formulas that we learned way back in Calc 1, Calc 2, and that's what I'm using right there. Okay, so let's erase that and let's do these integrals very slowly. So when I plug in 0 here, the first thing I'm going to get is I'm going to get 1 over n pi cosine of 0. And then it's going to be minus 1 over n pi cosine of negative n pi. So that's what happens for the first piece. And then the next one, I'm going to be very careful. I'm going to go cosine of n pi and then minus cosine of 0. And now I'm going to have a good understanding of the cosine function. First and foremost, what is the cosine of 0? Well, that's 1. So this is always going to be 1 over n pi. We'll factor that out. I should have never brought it out. And this is 1. Now, the cosine is an even function, which means cosine of negative input is equal to just a cosine of the positive input. So we can write this if we want it as this. Now, what you might say to yourself is you might say, well, how can I go further because I don't know what n is? Well, really, it doesn't matter, and there's two reasons it doesn't matter. The first reason it doesn't matter is what is the cosine of multiples of pi? Well, let's think about it. What's the cosine of 0? It's 1. What's the cosine of pi? Negative 1. What's the cosine of 2 pi? 1. Cosine of 3 pi, right? So what happens is with cosine of pi and cosine of integer multiples of pi, it's either plus or minus 1. The cosine of an integer multiple of pi is either plus or minus 1, which means this cosine right here is either plus or minus 1, and this one is either plus or minus 1. And guess what? Since their inputs are the same, then they're always going to be the same number. So if we write this out, this is nothing more than 1 over n pi minus cosine of n pi all over n pi minus cosine of n pi all over n pi. And then this is minus a minus is plus 1 over n pi. So that's one way to think about it. So let's think about what is cosine of n pi? Well, when n is even, when n is 0 or 2 or 4 or 6, these guys are always plus 1. And then when n is odd, like 1 or 3 or 5, then that number is going to be negative 1. And if you don't trust me, go to a calculator and plug cosine of 5 pi. It's going to give you negative 1. Type cosine of 37 pi. It's going to give you negative 1. So we have two cases here. And by the way, we can write this a little cleaner. Maybe I should have done this in the first place. Let's sort of rewrite this. Let's get the eraser out. Instead of distributing the 1 over n pi, let's bring it all out front. So if I bring that all out front, let's write it slightly different. It'll be a little more illuminating, I think. Maybe I should have done that in the first place. If I pull the 1 over n pi out, I have a 1 and a 1, so I get a 2. 1 minus a negative 1 is 2. And then I'm left with a minus 2 cosine of n pi. So this is going to be one of two things. So let's look at two cases. It's going to be one of two cases. So let's do the easy case first. Go to your calculator and type cosine of 4 pi, cosine of 28 pi, cosine of 50 pi. Anytime you take cosine of an even multiple of pi, you're going to get 1. So that's going to give you 2 minus 2, which is 0. So this is always going to be 0 when n is even. Okay, what happens when n is odd? When n is odd, you get negative 1 on that cosine. So you get negative 1 times negative 2, which is positive 2. So you get 2 plus 2, which is 4. So this becomes 4 over n pi when n is odd. And you really need to convince yourself of that. This is, now we're not doing baby stuff anymore. We're really getting your brain to work. We want you to really think. And convince yourself that that's 4 over n pi. Whoo, that's crazy. Does anybody have a question about this? So you can see that these are some tedious calculations. Okay, so what does all this mean? So let's summarize what we found. And please, if you have a question, do not hesitate to ask. These are some heavy computations. So in summary, a sub n equals 0 for n equals 0, 1, 2, 3 for all n. B sub n, what we found is the following. B sub n equals one of two things. It equals 0. That's a bad bracket. Let me fix this. It equals 0 when n equals 0, 2, 4, 6, 8, etc. But it equals 4 over n pi when n equals 1, 3, 5, 7, 9, etc. Whew, I'm having fun. Okay, so now we have to put this all together. So what is the Fourier series? Well, let's go all the way back to what we did on Wednesday. What is the definition of the Fourier series? The definition of the Fourier series is the following. So let's not write it, I guess we can write it compactly first. Remember what the Fourier series was. It's a sub n cosine of n x plus b sub n sine of n x. And so let's write it out. So you know what this is. This is a sub 0, and then there's no b sub 0. B sub 0 is always going to be 0, but I guess we can write it in anyhow. And then it's a sub 1 times cosine of x plus b sub 1 times sine of x plus a sub 2 times the cosine of 2x plus b sub 2 times the sine of 2x, and then this goes on in that pattern. And what did we find? Well, all the a's are 0, so all these terms go away. This guy's gone, gone, gone. So what remains? Well, the pattern is not hard to see as long as we're careful. What remains is b sub 1. So what's b sub 1? Well, that's 4 over pi sine of x. And then what's b sub 2? Well, that's 4 over 2 pi sine of 2x. And then what's the next one? Well, that's going to be 4 over the next even guy. Or excuse me, whoa. Slow down, over. B sub 2, we know this guy is, I'm getting ahead of myself. This guy goes away too. So what's the next guy that survives? So it's B sub, I got ahead of myself. Slow down. Only the odd guys are the ones that survive. So b sub 1 is that. Now what's the next one? It would be b sub 3. So that would be 4 over 3 pi sine of 3x. And then the next guy would be 5. So it'd be 4 over 5 pi sine of 5x plus 4 over 7 pi sine of 7x. Provided we didn't make a mistake. And of course, this pattern goes forever and ever and ever. Does anybody have a question about this? Now, that was a lot of computation, but it turns out that all that computation has a reward. Because when we start looking at the pictures now, it's going to be this really, really cool image. Before we do that, though, does anybody have a comment or a question about this? All right, so before I guess we could write this in a more compact way. So how could we write this compactly? So the Fourier series of this function, which we defined f of x equals -1 for x between 0 and negative pi, and then positive 1 for 0 less than x less than pi is this creature. So it's 4, everyone has a 4 over pi inside, and then it's times the sum. K equals 1 to infinity. Well, it's all the odd guys. So one way to write this is that it's the sine of 2k minus 1. This is going to look scary. X divided by 2k minus 1. So why is it 2k minus 1? Because we only want the odd guys. So when k is 1, you get 1. When k is 2, you get 3. When k is 3, you get 6 minus 1, which is 5. When k is 4, you get 8 minus 1, which is 7. So it'd be a great time now to go look at a picture. So I'm going to load that up. Does anybody have a question? And by the way, don't forget, let me show you what we're trying to mimic here. This is what we want to mimic. We want to get this kind of picture here. So let's do that. Let's make sure we're getting Desmos here. All right. So here's what we're going to do. We're going to start with our function. So I'm going to say f of x. That's what it is. And it is defined two ways. So in order to do a piecewise function, I'm going to have to be a little creative. I'm going to define this as 1. And when am I going to define it as 1? When 0 is less than x is less than pi. And then I'm going to have to give this another name. I'll call it g. We'll call this g, and this will be -1. And what is the domain here? Well, it's negative pi less than x less than 0. So let me change colors here so I'm matching. And let me move this around. So right now, hopefully you're seeing these blue lines. Now I can extend this. Let's change my pattern. I'm going to go from negative 3 pi. Nope. So let's say 2. I'm just changing my picture here a little bit. And I'm going to go from negative 3 pi and then to 3 pi. So now how do I extend this picture so that it looks like the one that I drew earlier? Well, I'm going to have to get creative. I'm going to have to say, let's just duplicate a couple of these things. So I want to duplicate this guy. Where does this guy go? Well, this guy goes, when is it 1 again? It's 1 from 2 pi to 3 pi. And where is it -1 again? If I duplicate this guy, it's 1 from pi to 2 pi. So I hope you're seeing this is probably not the best way to do it, but that's what we're trying to do. I don't know, maybe you can find a better way of doing it. And I can continue to duplicate this. If I duplicate the -1, whoops, that's not what I wanted. Cool, thank you, have fun. All right, I'll take care of it. Have a good time. You want to learn about Fourier series? Huh? All right, good talk. All right, Anyhow, so where else is this negative 1? Well, it's going to be negative 1 from negative 3 pi to negative 2 pi. And then, of course, we got to duplicate this guy one more time. And where is that going to be? That's going to be from negative 2 pi to negative pi. So hopefully you see the picture here with this sort of negative 1, 1, negative 1, 1, negative 1, 1. Whew. Okay, now the fun part. So let's switch back for a second. If you look at the homework, I asked you to graph f, which this is our function f. It just took me a bunch of ways to plug it in. And I want to graph it with the first 5 partial sums of the series. So let's do the first one. What was the first one? Well, the first one is just, let's cheat, not cheat, but let's think of everybody as a 4 divided by pi in front of it. So let's put this here. And what's the first guy? The very first guy was just sine of x. Right, so that doesn't look too great. So again, where am I getting this from? If I go back to my whiteboard, what's my first guy? My first term is 4 pi over sine of x. So that's the first term. Now, what happens if we add the second term? Well, that's the 3 term, that term. So if I go back here, let's put a parenthesis here, and then the next one is going to be, well, I guess I can't have a parenthesis. Yeah, I can. So now it's going to be sine of, I guess I need a plus sign, sine of 3x divided by 3. So now you're seeing that this green curve, again, what's it trying to do? It's trying to mimic these blue guys. So if I add the next guy, I forgot my, bear with me, I forgot. This should be over here. So that's the first 2 terms. What if I add the next term? Well, the next term is the sine of 5x divided by 5. And so I get this piece. So what you see we're doing is we're trying to approximate this discrete sort of signal, this discrete function, negative 1, 1, negative 1, 1. We're trying to find a continuous and smooth curve, this differentiable curve that is approximating it. And so what happens is we can keep adding terms. That's the first 3 terms. What if I add the 4th term, which is sine of 7x divided by 7? And then the next one would be sine of 9x divided by 9. And you start to see what's happening here. This is maybe if we change colors, it'll be a little better. Let's go blue, red. And you see the red and the blue. Does anybody have a question about this? This is wild. But at the same time, it's really, really useful. And there's so many cool things you can learn about this. You can think about it 2 ways. You can think about it as, okay, we have this very complicated wave. Look at this wave, this red wave. And one way you can interpret it is, okay, we're going to approximate this complicated signal with just this simple on, off, like a very simple wave or signal. And so it's kind of like, it's which way do you want to go? It's like you guys, everybody here knows, I think you guys know what a smoothie is. Like, you know, you go buy a smoothie, you put fruit and different things in, you put it in a blender and you mix it up and you have some smoothie. Well, that's one way to think about it. The other problem would be, given a smoothie, how do you determine what all the ingredients are? And so what this Fourier series kind of business does is it starts to show you a little insight into that sort of line of thinking. Given that blue graph, how do we approximate it with a nice, smooth, differentiable thing? Or given this really smooth, interesting red curve, how do we approximate it with something simple? So this is quite fascinating, and it's very useful. And by the way, we can do many more terms. If I come here, you guys maybe have seen this before. Let's just type it in the more compact way, which is pretty cool. Just like I wrote it on the previous page, what if I say sum? And now I go, let's use k because I used k before. K equals 1 to, let's say, we'll say n for now. We'll stop it somewhere. And what was our pattern? Our pattern was the sine of 2k minus 1 times x. And then that was divided by 2k minus 1. Not s. And then we can tell it what we want n to be. Suppose n is like, say, 2. And then we could start n, let's say 1, 2, let's say, I don't know, we'll start it at 10. And now we can animate this. What happens as n increases? You see the approximation in general seems to become much better. What if we went up to, say, 50? So, you can animate this if you want. As the number of terms increase, we get this pattern, although there's some really cool phenomenon happening here. You have this sort of when n is large, you get this sort of overshoot and undershoot, which can be studied. It's pretty cool. Does anybody have a question about this? Now, here's a cool question, and maybe you can start to you might start to think about this. One of the big questions that, and I know both of you had me in calculus too, when we were talking about Taylor series, the big question I posed, and I said, you really can't study it in calculus. You need to take higher courses. But the big question is, does a Taylor series converge to the actual function? And the answer is sometimes yes, sometimes no. But you'll notice here that when we wrote this down, I didn't say, if you look at this page, I didn't say that f of x is equal to this, because we don't know that this red curve, quote unquote, converges to the function. What we mean by that is we don't know that if I plug in x equals 3 into this series, I don't know that that's going to equal f of 3 in the limit. And in fact, if we look at this picture on Desmos, if we look at sort of what's happening here and here, we would imagine that this convergence question is very fishy, because it's not matching up the way we saw things matching up with like Taylor series, like with e to the x or sine or cosine. So we have this sort of almost like we're getting air here. Nonetheless, people, at some point we do study the convergence of these Fourier series, and it turns out to be very important in many applications. Okay, so here's something to ponder. This was a problem very similar to two of the things I asked you for homework, and you'll notice for us in class, it took us about an hour to do it. Right? I would have went a little faster on my own because I know some of the themes and the tricks. I know about when things are going to be 0 and when they're not. You don't know that yet. You have to practice. Nonetheless, you would imagine that for you to correctly get problems, what are they, 2 and 3, I think I asked? Yeah, 2 and 3. I asked you to do these for 2 different functions. It's going to take you a fair amount of time to get these correct. Now, the thing is, if you're good at searching, the internet, you'll find lots of very useful things for this. Like, I'm sure Wolfram can do these things for you. I'm sure some of those other pages, one of those like Simbo Lab and other things can do Fourier series. But, you know, if you're serious about learning this stuff, then what you have to do is you have to suffer through these calculations to get a feel for what's happening. At least that's my advice to you. Whether you take it or not, I don't know. But I think it's a great thing for you to practice and sort of see if you can get the answers to match. And then you can Google things like, why are Fourier series important, and all that fun stuff. Let's see, I'm going to actually try Wolfram right now. I wonder if it can do Fourier series of f of x equals, let's see if it does this one. It might. Yeah, Wolfram seems to spit it out for you. It's very nice of them. Oh, and here's another thing that you might want to try doing to really get practice. Instead of doing A sub n's and B sub n's, why don't you try doing the C sub n's and seeing if you get the same thing, which you should. So you might recall that we said there's 2 ways to define a Fourier series. You can use sines and cosines, or you can equivalently use the exponentials.
I had a question about the exponentials part.
Yes.
Like, I did not know what the IN meant. Are those just numbers? When we were doing Fourier series last time.
Say that again. The IN.
Yeah, like
No,
it was.
so I is the imaginary number. Have you ever worked with imaginary numbers? Like, do you remember those from like algebra?
No.
Okay, that's all fine. Maybe you didn't. Sometimes that's taught in school. Sometimes it's not. So don't get, you know, it's not like you're missing out, but it's something that you're going to learn about soon enough. So let's put it in this perspective. Certain numbers are intuitive to us, are they not? Like if you're a child and you're collecting toys, like my kid, you know, she's 2 years old, but she knows like what 3 means because she can count, you know, 1, 2, 3 dolls. Does that make sense? Like she gets that.
Yep.
You know, integers make sense to us as humans. But what we realize, whether we're solving real world problems or we're just doing math for the heck of it, like, you know, let's sort of like, am I sharing the screen? What am I? Oh my God, I'm hitting all kinds of crap. I'm giving pulls. No, I don't want to get this out of here. All right, we're on the whiteboard. So we understand integers, so it makes sense to us to solve, like, even humans had no problem, you know, solving equations like, you know, x minus 7 equals 3, because we're like, okay, obviously 10 is the answer, right? You're excited. It makes sense to us, and 10 makes logical sense to us. We can count. We can see that 10 has meaning. But even long ago, I mean, humans didn't really accept negative numbers because there's no concreteness to negative numbers. Like my kid's not going to get -3. You know, if I just switch this equation around and I said, okay, x plus 7 equals, say, 20, they might get that the answer, they might guess or check that, you know, 13 works. okay, and that's fine. But to them, the idea of, how would you first learn to do this as a student? You said, I'm going to subtract 7 from both sides, right? That's kind of what you're taught in school. And that's cool. So even though my kid doesn't know what -7 is, they understand that they can maybe take things away. But then your intuition is gone. If I change the problem to this, x plus 7 equals 5. Now it's real hard for someone who's young and hasn't done, say, basic algebra before to understand how do you represent -2? What does that mean? There's no concreteness to -2. However, we understand that if we want to solve equations, then we have to create these negative numbers. And they're not completely out of nowhere, right? I mean, we understand things like, okay, if there's a difference, Abdullah, between you owing me $5 or me owing you $5. So one way that we can incorporate who owes who is we can assign a sign to it, positive or negative. Just like if I say you're going 7 miles an hour, well, that's not as clear as it could be. 7 miles an hour where? Are you going this direction, that direction, whatever? And so what we do is we assign direction to things. And so if we even want to assign direction to something, we have to sort of generalize the numbers that we allow. We have to say, okay, even though our human mind can only concretely see integers that are positive, and I guess we can think of fractions as well, because I can take something and break it into equal pieces. So fractions are somewhat intuitive to us. But negative numbers are not intuitive. Irrational numbers like the square root of 2 is not intuitive to us, because you can't measure the square root of 2 on a roller. However, think of how this is such a mind, what? Take a square of side 1 and 1. Take this square, side 1 and 1. Now, if you went and took a roller, let me do this more clearly. So if I take a square and I say, okay, great, it has side 1 and 1. Okay, what's the diagonal? Well, the diagonal, and this was a problem that really stressed out the ancient cultures, because what they realized is that I can draw a line from here to here, and the scary thing about this line is its length is square root of 2. That's the Pythagorean theorem. But you can't measure the square root of 2. There's no concreteness to the square root of 2. It's the limit of something. So these irrational numbers that we study and we use, I shouldn't say study, we don't study them yet, but you use on a number line that fill in all the gaps, those are limiting values of much more complicated things. So even though we can't sort of concretely grab negative numbers or numbers like the square root of 2, like I can't have square root of 2 apples. That doesn't make any sense, right? But we realize that if we want to do mathematics, if we want to answer questions, then we have to allow these to be part of our number system. Okay, so it goes a step further. When you start studying quadratics, you get it to something like this. I want to solve this equation. Now, from an intuition standpoint, this equation should not have a solution. Let me explain why. You know that every number squared becomes positive. And so from your intuition, the same intuition that my 5-year-old has, there's no way I can add 2 things up that exist and that are positive. Like you can't take 4 dolls and add 1 doll to it and get 0 dolls. That makes no sense to our mind. However, if we want to develop a mathematical system that allows us to answer questions, we have to come up with meaning to this equation. And so what we do, if we follow the regular rules, we know that x squared is -1. And then x, by definition, is plus or minus the square root of -1. And so this is not a number according to what you were taught in school until you learn about the complex numbers. So what we do is we define what's called the imaginary unit, and we define it I. And what is I equal to? It's equal to the square root of -1. Now, what's really, really wild about this is humans just invented this. In many ways, and it's a very recent thing. It's only a couple hundred years old. Humans didn't want to accept saying that there's this complex number system or these imaginary numbers, because we would think that since we're just making them up, that they can't be used in the physical world. Well, here's what you're going to find out, Abdullah. When you start taking classes in engineering, and particularly things in like electrical theory and in many other places, not just electricity, in order for the theory to make any sense, we have to accept that there is a whole new number system out there called the complex numbers. Now, the real numbers that you're familiar with, the number line, it is a subset of the complex numbers. So every real number is a complex number, but not vice versa. And so what is a complex number? A complex number is this. Complex number would be something like A plus I times B, where A and B are real numbers. So the complex numbers turn out to be extremely important in engineering and in physics and in mathematics. And so what we do is we accept them, even though we can't concretely touch them, we accept them as part of our number system. And so one of the most fascinating things about these complex numbers is that they have this beautiful relationship, is that you can take the number e, and if you raise it to the power I times the variable x, this is always equal to cosine x plus I times the sine of x. Now, you might say to yourself, how is this possibly true? And there's lots of ways you can prove this or derive this. One way is to use power series. So if you remember from Calc 2, we had power series. And so if you take the power series for these guys, what's e to the ix? You guys will recall this from Calculus 2. This is 1 plus ix plus 1/2 ix squared plus 1/3 factorial ix cubed plus blah, blah, blah. Remember what the factorial thing is? And so this becomes 1 plus ix. And then one of the things you'll learn is that I squared, so if I is the square root of -1, then I squared is just -1. And so this I squared becomes -1, so this becomes minus x/2, and then this becomes, so what's I cubed then? I cubed, if you think about it, becomes -1 times the square root of -1, so that becomes -I. So this becomes minus I/3 factorial x cubed, and then this thing changes sign, and you can actually show that this equals cosine. You know, it takes a bunch of steps, but you can show that it equals this. It's not, you know, you might not remember any of this stuff, but you can do it if you wanted to. And this is going to seem overwhelming, Abdul, but we're trying to shove a bunch of stuff into a short period of time, and it's okay that you're not that familiar with it. I don't expect you to at this point. But if you're not comfortable with it, then you don't have to worry about the C sub n. You can just worry about A sub n and B sub n. But I only say this to you now because you're eventually going to have to do it anyhow, because you're going to be taking classes where this stuff is everywhere. everywhere, everywhere, everywhere. And the more classes you take, you're going to learn that these complex numbers are just another way to talk about a point in the plane. And then there's all these connections with sines and cosines. It's really quite fascinating. If I can just point that out real quick. Let's take a point in the plane. What does it normally have? It normally has an x and a y coordinate, right? So what if you drop down the perpendicular? And let's draw a triangle here. So let's color these triangles in differently. So you have a triangle, and then just from some basic ideas of trigonometry, if this is some angle theta, or x, whatever you want to call it, what do we know? Well, we know that x is equal to the cosine of theta. If this is, let's call this r. So what is the cosine of theta? It's opposite over hypotenuse. So, excuse me, adjacent over hypotenuse. So the cosine of theta is x over r. And then y over r is the sine of theta. But we can associate this point right here. We can associate this with the complex number z equals x plus iy. We can just say that there's some this is an association. Okay, so then what does that say about z? Well, that means that we can use this idea from calculus, this polar coordinate idea, and you can say that z equals r e to the I theta. And this is going to maybe not make sense right away. And again, I'm not even saying you have enough time in your life right now to think about this, but you can definitely do this. So this is what's called the polar form of a complex number. So anyhow, I don't want to go into too much of this because it's defeating the purpose of what we want to do right now. We want to study Fourier series. One way of doing it is to use these complex coefficients. If you don't feel comfortable with it, that's fine. You don't have to. You can do it the other way, A's and B's. Does that make any sense? I don't even know if that answers your question. But
yeah, it did.
did you guys ever do any of this in algebra before or no? I know some students do complex numbers and others don't. It just depends on who your teacher was.
They kind of did it for SATs, but
yeah, right. So that's right. Yep. All right. Any other questions on this? Okay, if you guys don't have any questions, well, I'm going to encourage you to work on these two. You know, the integrals are not that difficult, but they're the type of integrals that pop up when you're computing Fourier coefficients. So that's why I asked you to work on them. You know, if you look at problem 1, like problem 1A and problem 1C and F, don't worry about that I. You can just treat that as a number. You don't even have to think of it as the square root of -1. You know, so what I mean by that is if you look at problem 1A, if you want to integrate e to the -10 ix dx from, say, -pi to pi, just pretend that this is just the number. So what is this integral? Well, this, you know, what's the integral of e to the ax dx? You'll just remember it's 1 over a e to the ax, right? Plus c, of course. And so this becomes -1 over 10I, because that's the number in front. Then it's e to the -10ix from -pi to pi. And so when you plug this stuff in, you can leave the -1 over 10I out. When you plug in pi, you get e to the -10 pi I, if you want to write it that way. And then it becomes minus e. Now plug the negative pi in, it's just going to become 10 pi I. Okay, and so you can leave it like this, but you don't have to. You can now use that formula from the previous page. You know, if you want, you can write this as, if you want to write it in exponentials, that's fine, but you can also write it using sines and cosines. So this would be cosine of negative 10 pi I plus I sine, etc. So you could do that if you wanted, or you can just leave it just like this. That's good too. Doesn't matter how you want to do it. And in fact, a good way to learn is just to play around with it if you have the time. See what, if you can write it cleaner, if not, whatever. All right. Any other questions about this? So this stuff is a little challenging, but please work on it. That way, if you have any questions, we can talk about them on Wednesday. And then don't forget, we want to show you why this stuff is important. Why do we care about Fourier series with respect to this idea of, you know, studying models of the brain? So that's sort of where, you know, on Wednesday we would like to show why this can be used. Why is it useful, I guess is a better way of saying it. All right, so then I guess what we'll do is we'll end it here, and then you guys can please work on this, and if you have questions, you know, let me know. All right. All right. Well, listen, I will let you guys go then. Thank you very much, and if you have any questions or any issues, let me know. All right. All right, everybody, take care.